You know, AI is moving so fast these days. It's insane, and it's almost hard to get myself to spend time doing anything else than trying to just create the beneficial singularity as quickly as possible, like we could be in the last 1, 2, or 3 years before we get machines smarter than people. And I keep having to remind myself that, like, if I really work, you know, 120 hours a week on trying to build beneficial AGI, I'll probably turn myself into some kind of monomaniacal psychopath, which will not make me the right guy to be at the center of building the positive singularities. So, keeping it at 100 hours a week is probably for the better, and then spend time on other things that keep me a fully functioning human. For example, working with some cool people to create a 8.5 foot tall metal Goku made of old bicycle chains and machine parts. He's pretty cool, right? And playing with my kids, spending time with my wife, walking outdoors, playing music now and then. I mean, there's nothing more important on the planet now than making sure the coming transition to AGI and ASI is done the right way. But yet, as a human, you've got to remain a full-featured human to pull it off the right way, right? And with that said, I don't want to say wasting time, but I've been distracting myself a bit in the last month or so thinking about quantum computing, right? And you could say that, why worry about it? We're going to be able to build an AGI on classical computers, right? And if we build the AGI on classical computers, I mean, then that AGI itself is going to figure out quantum computing, right? I mean, it's going to figure out quantum hardware. It's gonna figure out quantum software. It's gonna do the whole thing, and that's probably correct. But yet, from a research point of view, it's nevertheless interesting to keep thinking about a diversity of related topics, and that is where creative insights come from. And even though I think we do have a quite good plan for building AGI with Hyperonic architecture plus predictive and causal coding neural nets, I mean, we still need some creative thinking along the way, right? So with that in mind, I've allowed myself to indulge here and there in some creative thinking on quantum computing. And one thing I've been thinking about is how to evolve novel quantum algorithms. I mean, there's not that many known sort of families of quantum algorithms out there, right? There's sort of a few basic ideas in quantum computing. There's cool ways to do factoring rapidly. There's ways to do database search in very rapid amount of time. There's some tricks for doing, quadratic function minimization. There's not nearly as wide a variety of different quantum algorithm families as there are classical algorithm families, for example. And I don't think that's because the quantum world doesn't allow you to do that many things, right? I think it's because our imaginations are impaired at manipulating and navigating the affordances of the quantum world. And with that in mind, it's interesting to think about how AI can be used to figure out new quantum algorithms, right? So I've been sort of piecing together different ideas in this regard, and I mean, I don't have that much time for this, so my role here is like throw together an approach and then give it to some other tech people with a physics and appropriate quantum computing background to try to make it actually work. Some things I try to actually make work myself. This probably won't be one of them, but what I'm thinking is you want to use evolutionary learning, because evolutionary learning is good at wild-ass creativity. I mean, evolution came up with us, right? So you want to use evolutionary learning. What do you want to evolve? Well, you want to evolve quantum circuits. Okay, there's something called the ZX calculus, which is very good at representing quantum circuits in an elegant way. And I happen to have worked out some ways to sort of use some interesting AI tools to normalize ZX expressions. So you can take various quantum circuits expressed in ZX calculus and kind of normalize them so that programs doing similar things, quantum programs doing similar things, will have a similar form in ZX calculus, right? So, okay, we want to use an evolutionary algorithm evolving, cleverly normalized ZX calculus expressions, but then evolution can be very slow, so you don't just want to do evolution, right? What you want to do is estimation of distribution algorithms. So you want to be doing evolution, right? But you want to juice up the evolution by doing some probabilistic analysis of which programs seem to be doing something like what you want and which programs don't, right? And that's what the Moses algorithm in Hyperon does. Now, in normal Hyperon, you can use PLN, probabilistic logic network reasoning, to help Moses do its probabilistic analysis of the distribution of fit programs versus unfit programs. PLN is probabilistic logic networks. However, I developed not long ago something called QLN, quantum logic networks. It's like PLN but using quantum amplitudes in place of regular probabilities. It's how you want to do probabilistic-like inference about, states and events in the quantum world. So the thing is, if you want to use something like Moses to evolve ZX calculus expressions representing quantum programs, to understand the distribution of fit quantum programs versus unfit ones, according to the fitness function you're using to drive evolution, you want to use QLN, quantum logic inference, for the estimation of distribution algorithm, right? So this I think is the way to do it, right? You want to do program evolution. We're using nicely normalized ZX expressions for the quantum program circuits. And then you want to accelerate evolution with an estimation of distribution approach. We're using quantum logic network reasoning to study the distribution of programs, right? And this doesn't need a fancy quantum computer, right? I mean, some folks on SingularityNet team working with me are playing with the Dirac 3 quantum computer for small problems, but that Dirac 3 can optimize like a function of hundreds of variables at a time, right? It can't do what we need to do to evolve novel quantum circuits. It's not big enough, but it's okay. You don't actually need a quantum computer to do this sort of evolution of new sorts of quantum programs, right? Like you can do this on a classical computer. You could do it even better on a quantum computer, and we can write out how, but you could do it now on a classical computer, and we could learn new types of quantum algorithms that have never been thought about before, right? Now, indeed, if we get a classical AGI program invented in a year or two from now, it will be able to figure all this out much better than I will, right? So in that sense, like, why bother? On the other hand, I have an inkling that something in this train of thought may even be useful for classical AI. I mean, I came to the conclusion last month that a sufficiently complex classical system should be modeling itself as a quantum system, as a corollary of the notion that a smaller classical system should often model a much larger, more complex classical system as quantum, because the internal states of the larger system are unknowable to the smaller system because it's so much smaller. In the same way, your deliberative reflective mind is much smaller than your unconscious mind, so your deliberative reflective mind should model your unconscious mind as using quantum algebra, right? So given that classical systems in some cases should be modeled by us or by themselves as quantum. You wonder if learning new quantum algorithms can also be a way of learning new algorithms for classical systems to interrelate their deliberative and their unconscious mind, right? So there's a lot of interesting things lurking around the edges here. Now, I think we're musing here about aspects of intelligence probably beyond what the human brain does. So again, like our task to build beneficial AGI is first to build something as generally smart as the human brain, not just at doing specific tasks, but being able to leap beyond its training distribution and imagine new stuff, but also compassionate, ethical, loving, and wanting to work with us to create a future that's good for everyone. Like that's the number one thing. We don't really need to invent new cognitive approaches way beyond the human level. On the other hand, it wouldn't hurt, right? And and what we see now with AI systems, even LLMs, is they're superhuman in some ways, subhuman in others, and the same will be true with Hyperon-based AGIs when we roll those out. And the pattern of superhuman and subhuman en route to achieving full-on human parity, and then going beyond the details of that aren't quite clear. Anyway, there's some things I've been musing about. I wrote out a technical paper on this approach to learning novel quantum algorithms, which I'll put in the description for this video, but it's fairly deep on the math. Here I've wanted to just get across some of the basic vibe of what I've been thinking about. Thanks for listening.